In fact, if later on where Professor Jack discussed about JPEG 2000, who have heard of JPEG before? I'm sure you know JPEG, right? JPEG 2000 based on wavelet. Okay, so when we discuss JPEG 2000 application of wavelet, you can see that one of the choice is a 3-5 system. And this is actually used in a standard based compression. The nice thing about this system is it's all integer values. Now integer is very good. Why integer is good?
Easy to compose.
It's very easy to compute, right? Because if you think about it, your image is an integer or floating point. If you take a look at an image, how many bits is in an image? 8 bits, right? It's a grayscale from 0 to 55. It's 8 bits. It's an integer format coming in. And the transformation that you use to analyze, if it's integer, it's very, very nice because you don't have to use a floating point processor. Okay? And it's also allowing you to have lossless compression because this particular transformation does not lose, you don't have to forget anything. Right? So it's allowed for lossless compression. It's very, very fast because all you have to do is integer-based, computation. Now, however, it doesn't. It's about 0.5 dB, slightly worse than the best choice. Okay, so I'm going to discuss another choice where it is used. It's called 97 wavelet. Okay. But basically, this is the choice that people use in JPEG 2000. This is also a very good choice. It is used in Ricoh. You know, Ricoh is the camera maker and the printer. They have their own compression engine, and they actually use this particular 2.6 in their compression. It's worked pretty well also. Okay, it's very, very fast, all integer-based algorithm, and it's also lossless. Now, losses is important in medical imaging because when you compress medical image, you don't want to lose anything based on liability or losses and so on. Okay, it's also good for manipulation because you don't want to lose any information when you manipulate the images. For compression, it's also okay. So, any question regarding this? This choice?
I have questions.
Yeah.
You just said that when you compute F0 and F0, we must maintain the orthogonal.
That's one choice. One choice, right?
Okay.
You have many choices. You can have orthogonality, or you can have symmetry. Or I have another example where it doesn't have to be any of this. Okay? So tell me, how do I distribute this? Here's another example. F0, P0, F0, H0. Okay? So use the same one here. C inverse. 4, 0, and pi. How do I distribute the 0 so that it's not orthogonal, it's not symmetric? So here we discuss, right, orthogonal, factorization, and symmetric. I want none of this.
Now here we distribute
So tell me how to distribute C and C inverse. Separately. Okay. So let's C here and C inverse here.
2-1 or 3-1 or
3-1. Okay. Good. Is this interface?
no.
Why not? You need a pair of 0, right? For the C. So this is obviously not the interface. Is this orthogonal? No. What's the fastest way to check if it's not orthogonal or not?
It's the order F not
Very good. They have to have the same order, right? We said that the order is exactly the same. And not the same order, right? This is order 2, that's order 4. And this is not useful in application. So you see that, you know, there are all the choices that you can factor, and it's not useful. Okay? Alright. So let me give one more example, and then we go on to the next topic, okay? On how to distribute this load. F naught. Okay? This example P naught is 8, 0, and minus 1. There are 6 zeros elsewhere. There are 2 zeros here, and there are 4 zeros there. It's not important right now exactly where it is 0. And I know that P naught is limited. What is the order of P naught? 40. That's the number of zeros that we have, right? You have 6 plus 8 is 14. Okay? And we know that, okay, this is linear phase. These are pairs, right? Where are the other pairs? Are these 4 related in any sense? They have to be, right? If this is Z0, where's Z0 inverse? Is it here, here, or here? Is it 1, 2, or 3?
1, 3.
Not here, right? Because Z0 inverse have invert phase. You flip the phase, you should flip the radius, right? So inside go outside, and the phase flip. So this pair go together, and this pair go together. And the fact that they are complex conjugate also tell us that it's linear phase and real coefficient, right? Because real coefficient means that this and this have to go together as complex conjugate pairs, and this go together as conjugate pair. So it's not only linear phase, but it has real coefficient also. And any question on that? Linear phase because there are 3 pairs of inverted zeros. It's 1, here is 2, and here is 3. Real coefficient because the zero either on the real axis or are complex conjugate pairs, right? The real axis, pairs, pairs. Okay? All right. So if I want a polynomial, how many choice do I have for polynomiality? Give me one way to do it. How do I deal with 8, 0 here? 4 and 4. I know that I have to distribute them equally. Okay? How do I deal with this 6, 0? If I put 1, this guy here, where this one go? In the other side, right? How about this pair?
One inside.
One inside, one is outside. Okay? What do I do with this pair? One inside, one outside. This kind of distribution guarantee that for every zero, Z0 in here, Z1 in here, the invert in the other side. That's what we need. Okay? Z1, 0 in here, Z1 inverse. The inverse in the other side.